All right, so our algorithm is run length encoding. The idea behind this algorithm is that it takes the bitmap for things like videos or images and compresses them. So in this case, we have a grid that's converted into just a string based on everything in the grid, and then the sequential characters are compressed using the initial character and then just how many there are. And in our first version, the idea is that we just take a block of 4 that's scooted along the original string, and we compare whether there's a match in 2 characters, and we'll increment an integer as you see in like the bottom lines 2, 3, 4. This is dynamic programming. It takes a Turing machine approach, and that will allow us to sort of save on memory. And there's only a single loop, which we see here in the 4 bk in range line there. And then we use match statements. In version 2, instead of starting at the end and using a block of 4, we use just 2 characters. We have an initial character. We scoot the right character over until it doesn't hit a match. And as we hit non-matches, we add however many of each character to an array. Now, in this case, please ignore the fact that these S's are here. That was my bad. Those actually should not be part of this string. But this one does take more memory because we have a list of lists instead of just the original strings. We'll have both. But we'll get into that. Here's the code for that. Again, recognize the for loop. That's important because that'll go both from memory and space. And we have time complexity.
On to the time complexity. As for that, with algorithms, time complexity is the amount of time taken by an algorithm to run as a function of the length of the input. We found that the algorithm runs in O of n. For run length encoding, the input is a bitmap of characters or bits, as explained previously. When we looked at the code earlier, we also saw that both versions had one for loop that loops through the grid based on the length of the bitmap, which is represented by n in the time complexity. Since there are no other pieces in the code that affected the time complexity, we came to the conclusion that the time complexity is O of n.
For space complexity, we're worried about how much space we are taking up in memory. The worst case scenario for storage in this case is that there are no runs in the bitmap, meaning that each character is followed by a character that is different than it. For the first version, it was pretty simple. It only had the 3 initial S's that were appended to it for the Turing machine, and then the number of characters that were inputted in the bitmap. So it never increased the size over that. For the second version, it is quite a bit larger because we're storing that information in an array in addition to the string that we're iterating through. In either case, this ultimately bottles down to a linear relationship, though in practical terms, the second version is worse in regards to memory.
Joanna?
You might be muted.
Sorry, I was muted and speaking. So in comparison, version 1 starts back to front, comparing the first 2 characters of a block, then the last 2, and it updates the whole block directly. As version 2, it starts from front to back, comparing the first 2, then scoots the right pointer over, incrementing till it reaches a different character, and adds the result list at that time. In the graph, we can see that the memory assessment version 1 is better than version 2. And then in the operation assessment, we can see that version 2 is slightly better than version 1. And in summary, if the goal is to reduce memory, using version 1 would be the better option. In contrast, version 2 requires slightly fewer operations, which could increase speed there a little. But both are time/space complex at ON, so checking the total performance would be key to deciding which to use based on memory and computational performance. And here are our references.